Imagine Earth as a giant magnet. This isn't just a metaphor, it's a fundamental truth about our planet. The Earth generates a magnetic field that extends from its interior out into space, creating a protective bubble around us. It has a north and south magnetic pole, just like the magnets we use every day. These poles are where the magnetic field lines converge and are strongest. If you've ever played with a bar magnet, you know that opposite poles attract and like poles repel. This same principle applies to our planet on a much grander scale, but our planet's magnetic field is invisible. We can't see it with our eyes, but we can observe its effects. This invisible force is constantly at work, influencing everything from animal migration to human navigation. It acts as a shield, protecting us from harmful radiation from the sun. The sun emits a stream of charged particles known as solar wind. Without Earth's magnetic field, these particles would strip away our atmosphere, making life as we know it impossible. This magnetic field is vital for life on Earth. It not only protects us from solar radiation, but also helps maintain our atmosphere. Without it, Earth would be a barren, lifeless rock, much like Mars. The magnetic North Pole is not the same as geographic north. Geographic north is a fixed point, located at the top of the world, where the Earth's axis of rotation meets its surface. It's the point we think of when we talk about the North Pole. Geographic north is a fixed point marking the top of our planet. It's the point where all lines of longitude converge, and it's used as a reference point for navigation and mapping. Magnetic north, however, is constantly on the move. This movement is natural and has been occurring for as long as the Earth has had a magnetic field. The magnetic North Pole drifts due to changes in the Earth's core, where the magnetic field is generated. It's been happening for billions of years. By studying ancient rock formations, scientists have discovered that the Earth's magnetic field has flipped many times throughout its history. These flips, known as geomagnetic reversals, are recorded in the magnetic minerals found in rocks. Understanding why and how it moves helps us navigate, protect our technology, and learn more about our planet's inner workings. Modern navigation systems like GPS rely on accurate knowledge of the Earth's magnetic field. Scientists also study the magnetic field to learn more about the Earth's core and the processes that generate this vital force. Many animals, such as birds and sea turtles, use the Earth's magnetic field to navigate during their long migrations. They have a natural ability to sense the magnetic field, which helps them find their way across vast distances. The interaction between the solar wind and the Earth's magnetic field also creates beautiful natural phenomena like the auroras. These stunning light displays, known as the northern and southern lights, occur when charged particles from the sun collide with atoms in the Earth's atmosphere, causing them to glow. Scientists continue to study the Earth's magnetic field to understand more about our planet's core. The movement of molten iron and nickel in the outer core generates the magnetic field, and changes in this movement can affect the field's strength and direction. Throughout history, humans have relied on the Earth's magnetic field for navigation. Early explorers used compasses to find their way across uncharted seas, and today, advanced technology continues to depend on this invisible force. Educating the next generation about the Earth's magnetic field is crucial. Understanding this fundamental aspect of our planet helps us appreciate the delicate balance that makes life on Earth possible. The Earth's magnetic field is more than just a scientific curiosity. It's a vital part of the interconnected systems that sustain life on our planet. By studying and understanding it, we gain a deeper appreciation for the complex and dynamic world we live in. Deep within Earth lies a molten core, a place of intense heat and pressure. This core is not solid, but rather a swirling, churning mass of molten iron and nickel. Imagine a vast ocean of liquid metal, constantly in motion, driven by the immense heat from the planet's interior. This swirling mass of liquid iron and nickel is in perpetual motion, creating a dynamic and ever-changing environment. The movement is not random but follows complex patterns influenced by the rotation of the Earth and the heat escaping from the core. As this molten metal moves, it generates electric currents. These currents are crucial because they give rise to our planet's magnetic field. The process is similar to how an electric generator works, where motion creates electricity. In this case, the motion of the molten iron and nickel generates a magnetic field that extends far into space, protecting our planet from harmful solar radiation. Think of it like a giant dynamo, a massive generator at the heart of our planet. This dynamo effect is what creates and sustains Earth's magnetic field. Without it, life as we know it would be very different, as the magnetic field plays a crucial role in shielding us from cosmic and solar radiation. The flow of this molten metal is chaotic and ever-changing. It's a turbulent environment where the liquid metal moves in complex patterns, influenced by various forces. This turbulence is not just random chaos. It follows certain physical laws and principles, creating a dynamic and constantly evolving system. This turbulence causes fluctuations in the magnetic field, leading to the movement of the magnetic North Pole. The magnetic North Pole is not fixed, it wanders over time due to the changes in the flow of molten metal within the Earth's core. These fluctuations can be measured and tracked, showing a fascinating dance of magnetic forces beneath our feet. It's like a river current pushing a buoy along, constantly shifting its position. Just as a buoy moves with the flow of water, the magnetic North Pole moves with the flow of molten metal. This movement is gradual but continuous, reflecting the dynamic nature of the Earth's interior. The strength and direction of the magnetic field are not uniform. They vary depending on the location and the underlying movements within the Earth's core. This variability means that the magnetic field is a complex and ever-changing phenomenon, influenced by the intricate dance of molten metal beneath the surface. This unevenness also contributes to the wandering nature of the magnetic North Pole. The pole's movement is not a straight line but a meandering path, influenced by the shifting flows within the core. Scientists study these movements to understand the underlying processes and predict future changes. It's a complex dance of forces, driven by the heart of our planet. The interactions between heat, pressure, and the Earth's rotation create a dynamic system that is constantly in flux. This dance of molten metal and magnetic forces is a fundamental aspect of our planet's behavior, shaping everything from navigation to the protection of our atmosphere. Scientists use a global network of observatories and satellites to monitor the Earth's magnetic field. This network spans across continents and oceans, creating a comprehensive system that allows scientists to gather data from every corner of the globe. The observatories are equipped with advanced technology, enabling them to detect even the slightest changes in the magnetic field. Satellites orbiting the Earth provide a bird's-eye view, capturing data that ground-based observatories might miss. Together, these tools form a robust system for monitoring our planet's magnetic environment. These sophisticated instruments measure the strength and direction of the magnetic field at various locations. Magnetometers, for instance, are crucial in this process. They are highly sensitive devices that can detect minute variations in the magnetic field. Scientists deploy these instruments in strategic locations to ensure comprehensive coverage. The data collected by magnetometers is then transmitted to central databases where it is analyzed. This analysis helps scientists understand the behavior of the magnetic field over time and across different regions. The precision of these instruments is vital for accurate data collection and analysis. Imagine these instruments as buoys scattered across the ocean, each reporting the current's strength and direction. Just as ocean buoys provide critical information about water currents, magnetometers and other instruments offer insights into the magnetic currents flowing through the Earth. These instruments are strategically placed to cover vast areas, ensuring that no significant changes go unnoticed. The data they collect is like a continuous stream of information, painting a dynamic picture of the Earth's magnetic field. This analogy helps us understand the importance of widespread data collection in monitoring complex systems. By analyzing the data from these instruments, scientists can track the movements of the magnetic North Pole. This pole is not fixed. It moves due to changes in the Earth's core. Tracking its movement is crucial for navigation and understanding the underlying geophysical processes. Scientists use sophisticated software to visualize the data, creating maps that show the pole's trajectory over time. These visualizations help in predicting future movements and understanding the factors driving these changes. The ability to track the magnetic North Pole is a testament to the advancements in scientific research and technology. This constant monitoring is crucial for updating navigation systems, ensuring accurate compass readings, and understanding the dynamics of our planet's magnetic field. Navigation systems, whether in ships, airplanes, or smartphones, rely on accurate magnetic data. Any changes in the magnetic field can affect these systems, making regular updates essential. Scientists work tirelessly to ensure that the data is up to date, providing reliable information for navigation. Additionally, understanding the dynamics of the magnetic field helps in predicting geomagnetic storms. which can have significant impacts on technology and communication systems. It's like keeping a finger on the pulse of a constantly changing system. The Earth's magnetic field is dynamic, influenced by various factors both within and outside our planet. By continuously monitoring it, scientists can detect anomalies and predict potential disruptions. This proactive approach is akin to a doctor monitoring a patient's vital signs, ready to respond to any changes. The data collected not only helps in immediate applications like navigation, but also contributes to long-term research, enhancing our understanding of the Earth's magnetic environment. This ongoing effort is crucial for both practical applications and scientific discovery.